by the triangle inequality. The expectation of y2 is greater than or equal to the expectation of 1 over x squared minus x minus a half. We could separate these out with linearity of expectation and actually just get rid of this on the right hand side. If we're subtracting the positive part, this is greater than or equal to just the expectation of 1 over x squared. Of course, those absolute value signs are also unnecessary because the squaring makes it positive. This is equal to the integral from 0 to 1 over x squared dx, which is infinity. So y2 is not integrable, and therefore y is not a martingale. Now for part B, we shall first check that tau n is a stopping time for each natural number n. So let's fix an n in the natural numbers. And note that since tau n is greater than or equal to 1, we already have that the event that tau n is less than or equal to 0 is the empty set, which is contained in F0. So next, we note that since x is F1 measurable, we have that the event that x is less than 1 over n is in F1, since this is the pullback by x of a measurable set in the reals, and so this whole set is an element of F1, since x is F1 measurable. Therefore, we can write the event tau n less than or equal to 1 equal the event that x is less than 1 over n in F1, this just being by definition of tau n, and the event tau n less than or equal to 2 is almost surely, well, it's not even almost sure, it just happens for every single omega, it's equal to omega, and it's therefore contained in F2. So we have that tau n less than or equal to k is in Fk for every relevant k, which for us is 0, 1, and 2. So for every n in natural numbers, tau n is a stopping time. Now, since the random variable, which is the indicator that x is greater or equal to 1 over n, is less than or equal to the same, but for x greater or equal to 1 over n plus 1, we see that tau n is for the sequence of tau n's for all the n's in the natural numbers is increasing. Further, for every element of omega, there exists an n in the natural numbers such that x at omega is greater or equal to 1 over n. That's simply because x of omega is a single fixed positive number. So of course there is a 1 over n that's smaller than it. That n depends on the choice of omega. Therefore, the limit as n tends to infinity of tau n, omega is equal to 2 for every omega. That is, the sequence tau n increases to 2. Finally, we can observe that the probability that tau n is equal to the probability that x is greater or equal to 1 over n, which is equal, from the definition of x, 1 minus 1 over n, which tends to 1 as n tends to infinity. Now in part C we shall prove that the stopped process is a martingale. So fix a natural number and note that at time 0 the stop process and the unstopped process are the same, they're just both equal to 0. At time 1 the result is the same because tau n is greater or equal to 1. And at time 2, which as we saw in part A is the problem time for y, the stop process has a value of y1 if x was less than 1 over n, because then the stopping time tau n will be equal to 1. And as value y2 if x was greater or equal to 1 over n. That is x plus 1/2 common to both parts plus b over x squared, which only appears in y2. It is clear that the process y stopped at time tau n is adapted, and y tau n at time 0 and y tau n at time 1 are both integrable, because y is also integrable at both of those points. And that follows because x is bounded. Further from that, we can compute sorry if you can hear my cat in the background, it's being noisy. The expectation of the absolute value of y, the stopped process, y tau n at time 2. We can again do the same magic as we did in part A, but, well, no, similar magic, but slightly in reverse. So this was going to be less than or equal to the expectation of the absolute value of the component parts, but now split up and summed rather than taking the difference. On the right hand side we've taken the absolute value inside, that's why this b has become 1, because it's either 1 or minus 1, so in both cases it has absolute value 1. This now on the left hand side is finite because x is bounded, that is a given, and this expectation on the right hand side is equal to the integral from what we had before was the integral, where am I? From 0 to 1 over 1 over x squared. But because we're integrating over this indicator that random variable is greater or equal to 1 over n, this is now the integral from 1 over n to 1 of 1 over x squared. So this is this guy, which is also less than infinity, so the whole thing is less than infinity, and y tau n, the stopped process, is integrable. Now it remains to check the martingale condition. the expectation of y tau n at time 1, given f0, the trivial sigma algebra, is equal to the expectation of x minus a half. The expectation of x is also 1/2 because it's uniformly distributed over the interval 0, 1. So this whole expectation is equal to 0, which is also equal to y tau n at time 0. Further, since x is f1 measurable, the stop process at time step 2, given f1, is equal, well, just writing it out first, as we calculated before, every thing here is f1 measurable except for b. So we can take all of these random variables out of the conditional expectation except b. This of course all holds almost surely because we're just working with conditional expectations here. Since b is independent of x, it is also independent of f1, and therefore the expectation of b given f1 is just equal to the expectation of b, which is equal to 0. All this almost surely. Thus, the stop process is a martingale.